In this lecture, we'll see an example of an analysis of performance or evaluation of performance of the current transformer. So the question is, evaluate the performance of the multi-ratio CT in the following figure 2.1 with a 100:5 CT ratio for the following secondary output currents and burdens. Three cases are shown here. In the first case, I dash equals 5 amps and ZB equals 0.5 ohms. That is, I dash is the current that is seen by the relay, which is 5 amps, and ZB is the impedance of the instrument. It can be the relay. So that is a burden, which is 0.5 ohms. Now three values are given. I dash equals 8 and ZB equals 0.8. I dash equals 15 and ZB equals 1.5. So we are asked to compute the CT error for each output current I dash, as well as we are asked to evaluate the performance of the multi-ratio CT. Let's see the solution. Now, figure 2.1, as I already told you in the last lecture, it is the excitation plots taken from the Westinghouse relay manual. So for different CTs with different current ratios, we have secondary exciting volts versus secondary exciting amps. So if we know E dash, the corresponding IE value or the excitation current value could be found out from this particular plot. And in the question, it is given that the CT ratio is 100:0.5. So this one is the CT. Okay, so the corresponding secondary resistance is 0.082. Secondary resistance is Z dash, or secondary impedance is Z dash. Here it is resistance. What is given is resistance. So the total impedance will be Z dash plus ZB, burden plus leakage impedance. So 0.082 plus burden. Burden is also given in each case. 0.5 ohm is the burden. So 0.5 plus 0.082, which is 0.582, is the impedance, total impedance. This one. Z dash plus ZB, 0.082 plus 0.5. Okay. Now, I dash equals 5 amps. It is given. E dash equals Z dash plus ZB into I dash. The total impedance into I dash, which is E dash. So 0.582 into 5. This is given 5 amps, which is equal to 2.91 volts. Now you know the value of E dash. Corresponding IE or the excitation current can be found out from the plot for 2.91. See here, this is 2 and this is 3, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is 2, this is 3. So just below 3 is 2.91, right? So this will, corresponding to this value, we'll take the excitation value from the 100:5 plot. This is the 100:5 plot. So this is the point. Okay, at this point you take the IE value. So this is 0.2 and this is 0.3. So in between 0.2 and 0.3, somewhere between 0.2 and 0.3. It cannot be found out exactly from this plot, but if this is asked in the exam, specific points will be given. I mean, points will be marked accurately. Okay, here I think the gap is a bit long, so it's a bit difficult to find out the point. So in between 0.2 and 0.3. So it is taken as 0.25 here, 0.25 amps. So the IE corresponding to E dash, 2.9 volt E dash is 0.25 amps. Now you need to find the total current. Total current. What is the total current? Total current in primary. If you want to find the total current in primary, IE plus I dash is, what is IE plus I dash? I dash is 5 amps, 0.25 is IE. So the total secondary current is 5 plus 0.25, which is 5.25. And the turns ratio is given, so you can find the primary value. So 5 plus 0.25 into 100:5, right? 100 by 5, which is equal to 105 amps. Now you need to find the CT error. CT error is IE divided by IE plus I dash into 100%. in percentage we will get the CT error, which is 4.8%. So what does this mean? If your IE value is more, if your IE value is very high, that means your I dash value will be, what is your I dash value? IE plus I dash minus IE, right? So if the excitation current is very high, then the I dash value will not reflect the actual full secondary current, because of maybe the reason maybe it might have already entered into the saturation region. The current transformer might have already entered into the its saturation region. So for very high IE values, you may get the same E dash values, right? A proportionate production of flux may not be there. So that may be the reason for a high CT error. So this is the CT error. Now, as homework, you repeat the procedure for B and C. The values are given for B and C here. You repeat it, and on Friday's session, we will discuss this. Thursday night, you can submit the homework. So the second question is also a homework. The second question is, an overcurrent relay set to operate at 8 amps is connected to the multi-ratio CT in figure 2.1, the same excitation curve taken from the Westinghouse relay manual. With a 100:5 CT ratio with the same current ratio, will the relay detect a 200 amps primary fault current if the burden ZB is 0.8 ohms in the first case, and in the second case 3 ohms. Okay, so please do these two questions as homework. Homework 1 is part B and C, and homework 2 is example 2. Okay, now metering CT. What is metering current transformer? Metering current transformer is designed such that in case of faults, that means the primary current is very high, it will saturate. If the device saturates, that means IE value will be very high and I dash that is seen by the metering instrument will be very small. That is what is the purpose here, because the metering instrument should not carry a high current. So the device basically the device should operate in the saturation region. So thus save the instrument connected to its secondary from damage due to excessive current. So we'll see the BH curve. In the BH curve, the metering CT's operating point is in this region, that is in the saturation region. You know that H is proportional to I, right? So for high IEs, for E dash values here, for any E dash values here, we have high IE values, right? In this region, the range of E dash is very narrow, but the IE range is broad, right? A wider range is there for IE. So the excitation current will be very high, so that I dash is very small in this region. That means the metering CT carries a low current. So this is the region for metering CT, and this is the region for the linear region corresponds to the protective CT operating range. Now, in the coming lectures, we will go through the following topics: overcurrent protection of transmission lines, distance protection, differential protection, generator protection, transformer protection, bus bar protection, and numerical relays. Thank you.